Okay, another example looking at the theory of diffusion-controlled reactions. Can we accelerate a diffusion-controlled reaction by stirring? Okay, well, Wikipedia says yes. But let's look at this question more carefully. We can likewise think of this as the answer to a question about can we accelerate nucleation by stirring? Now I want to say that we are really talking about the molecular scale here, specifically the molecular scale. If I begin to talk about colloids and polymers, the answer might be different. The effect of stirring and convection will become important relative to Brownian motion and diffusive processes when the Peclet number reaches about 1. Okay, so let's remember what the Peclet number is. We have a length scale, we have a characteristic velocity, and we have a diffusivity. Okay, so this is going to define our Peclet number, and this is going to quantify the relative importance of convection to diffusion. All right, so now what we're going to do is we're going to let L be the diameter of a molecule. We'll take this to be the diameter of each of our reactants, okay? And we're going to let this diffusivity be the diffusivity of these molecules. Okay, and now what is the characteristic velocity? That's not intuitively obvious, perhaps. What is the appropriate velocity to use in this case? Well, these two molecules, the whole point of stirring is to create shear in the fluid, right? So I've got a molecule here that has diameter d, and let's suppose that I have another molecule here that has diameter d. Forgive my drawing. All right, that's the center of my two molecules. And so the distance between the centers is this length scale L. Okay, it's two half diameters added together. All right, now if I'm a molecule in a stirred fluid, all I feel is the local shear, and so the velocity here is going to be equal to the shear rate times the distance between the two centers. Okay, where that shear rate is going to be the gradient of the velocity with respect to distance between the two molecules. If this is my x-axis this way, then I'm looking at the gradient in this velocity along that direction. Okay, so this means that my Peclet number is going to be L times the gamma divided by d, or gamma L squared over d. Okay, so remember that when the Peclet number is equal to 1, we will have stirring become important. Okay, stirring is going to help these molecules encounter each other more quickly than diffusion would when the Peclet number is equal to 1. Okay, so for the Peclet number to be 1, then we want to set 1 to be equal to the size of my molecules, and let's say that my molecules are about 1 nanometer across. So these are small molecules, no bigger than that. So I have 10 to the minus 9 meters, that's my nanometer. That's going to be squared. I'm going to multiply by my shear rate, gamma dot, and I'm going to divide by the typical diffusivity for a small molecule in solution, which is always on, if it's an aqueous solution, is always on the order of about 10 to the minus 9 meters squared per second. And so if I go through and I simplify these things, I get that this equation tells me that my shear rate must be about 10 to the 9 per second. Okay, now that's a lot of shear. Okay, so if the fluid layer is just a few centimeters wide, you now have like relativistic velocities, velocity differences on the opposite sides of this rheometer. Okay, so that's an impossibly high shear rate. And so the answer for small molecules is no. Okay, so why does Wikipedia say yes? Well, it's easy to get confused about the difference between a diffusion-controlled reaction and a mass transfer limitation. Okay, mass transfer limitations are set by length scales of large objects, for example, a boundary layer, in the solution, whereas the length scales of molecules themselves are much, much smaller things, and they just aren't big enough to be affected by the macroscopic flow properties in the solution.